As we know, Chapter 1, full of holes, lacks mathematical support. Our comprehension of the universe, as it currently stands, harbors a profound paradox. On one side, we have quantum physics, which is like a detailed guidebook for tiny particles and the forces that they use to interact with each other. On the other hand, we have general relativity, which, with equal success, describes the way that matter and energy move through space and time, as well as how space and time themselves evolve in the presence of matter and energy. Each theory works great on its own, but when we try to use both at the same time, things get messy and confusing. For more than a century, scientists have been on a quest for a theory of everything, a comprehensive solution that would not only reconcile this puzzling contradiction between quantum physics and general relativity, but also make sense of all the forces, particles, and interactions in the universe through one all-encompassing equation. String theory is one such proposed solution. It suggests that everything in the universe, at its most basic level, is made of tiny vibrating strings of energy. Well, it's a theory that tries to answer the question, what are the basic, fundamental, indivisible, uncuttable constituents making up everything in the world around us? The idea is like this: so imagine we look at a familiar object, just a candle and a holder, and imagine that we want to figure out what it is made of. So we go on a journey deep inside the object and examine the constituents. So deep inside, we all know, you go sufficiently far down, you have atoms. We also all know that atoms are not the end of the story. They have little electrons that swarm around a central nucleus with neutrons and protons. Even the neutrons and protons have smaller particles inside of them known as quarks. That is where conventional ideas stop. Here is the new idea of string theory: deep inside any of these particles, there is something else. The something else is this dancing filament of energy. It looks like a vibrating string. That's where the idea of string theory comes from. And just like the bow vibrating strings that you just saw in a cello can vibrate in different patterns, these can also vibrate in different patterns. They don't produce different musical notes, rather, they produce the different particles making up the world around us. So, these ideas are correct. This is what the ultramicroscopic landscape of the universe looks like. It's built up of a huge number of these little, tiny filaments of vibrating energy, vibrating in different frequencies. The different frequencies produce the different particles. Different particles are responsible for all the richness in the world around us. And there you see unification, because matter particles, electrons and quarks, radiation particles, photons, gravitons, are all built up from one entity. So matter and the forces of nature all are put together under the rubric of vibrating strings. And that's what we mean by a unified theory. And here is the catch: when you study the mathematics of string, there you find that it doesn't work in a universe that just has 3 dimensions of space. It doesn't work in a universe with 4 dimensions of space, nor 5, nor 6. Finally, you can study the equations and show that it works only in a universe that has 10 dimensions of space and 1 dimension of time. The extra dimensions are thought to be compacted or hidden from our perception. Despite the allure of string theory's elegant mathematics and unifying potential, it has yet to provide testable predictions or experimental evidence, leading some to question whether string theory is dead or still a viable candidate for the theory of everything. You say the problem is just hard rather than we are barking up the wrong tree. So that's kind of how I think about it. Plus, it assumes that there's a fun, coherent, theoretical understanding of all phenomena in the universe. It assumes that, and you're putting your philosophical mission statement on the universe that you're investigating. And the history of that exercise has never proven to be successful. So I'd just like to take a step back and stay open to the possibility that there's a whole other idea that could supplant everything they're doing, that wouldn't take 30 people, 40 years to try to figure it out, because that's a lot of brainpower going in there. In all fairness to them, they made certain progress with their string theory in using it to interpret things that we now understand more deeply. Okay, so that works. And by the way, how close are we to proving it experimentally? You can have a hypothesis that is untestable in its core, but if the hypothesis is true, some other things might be true that you can then test. So you can test the edges of it. That can still make progress on the thing that you're waiting to test. If you can't do it today, testing for the existence of hidden dimensions is a complex problem and a major challenge in theoretical physics, especially given that many theories which propose these dimensions like string theory suggest they are incredibly small, possibly compact, and inaccessible through conventional means. If I take the most straightforward approach to string theory, you really are imagining that these dimensions are there. They're real. I mean, just as you would say that the three space dimensions around us, left, right, back, forth, up, down, they're real, they're here, we are immersed within those dimensions. These other dimensions are as real as these, with the one difference being their shape and their size differ from the shape and size of the dimensions that we have direct access to through human experience. And one approach imagines that these extra dimensions are tightly curled up, crushed together, if you will, into a beautiful geometrical form that's all around us, but just too small for us to detect with our eyes, too small for us to detect even with the most powerful equipment that we have. Nevertheless, according to the mathematics, the size and the shape of those extra dimensions leave an imprint in the world that we do have access to. So one of the ways that we have hoped yet to achieve to make contact with experimental physics is to see a signature of those extra dimensions in places like the Large Hadron Collider in Geneva, Switzerland. When you slam protons together at very high speed at the Large Hadron Collider, if there are these extra dimensions and if they have the right form, and that's a hypothesis that may not be correct, but when the protons collide, they can create debris, energetic debris that can, in some sense, leave our dimensions and insert itself into the other dimensions. And the way you'd recognize that is there'd be more energy before the collision than after the collision, because the debris would have taken energy away from the place where our detectors can detect it. So that's one real concrete way that you could find evidence for extra dimensions. And it hasn't happened yet. Doesn't mean it won't happen, but that would be a stunning moment in the history of the species if data that we acquired in these dimensions gives us kind of incontrovertible evidence that these dimensions are not the only dimensions. I mean, how mind-blowing would that be? Despite decades of research, string theory hasn't yet provided a single prediction that could be experimentally verified. Is the string theory dead? It's a question many have asked due to the theory's glaring predicament, lack of empirical evidence. Now, that doesn't mean it's a scientific dead end. Quite the contrary. As a field matures, you need to judge it by a different standard. You need to judge it by, is it making progress on foundational issues, deepening our understanding of the subject? And by that measure, string theory is scoring in very high. Now, at the same time, you also need to judge whether it makes contact with experiment too. And in that measure, we're still challenged. So I would say that many string theorists, myself included, are very sober about the theory. It has the tremendous progress that it had 30, 40 years ago that hasn't gone away. But we've become better equipped at assessing the long journey ahead. And that was something that we weren't particularly good at back, say, in the 80s. And that's the nature of science, quick hits that resolve everything, few and far between. And so if you were in for the quick solution to the big questions of the world, then you would have been disappointed. And I think there were people who are disappointed and moved on and work on other subjects. If you're in the way that Einstein was in for a lifetime of investigation to try to see what the answers to the deep questions would be, then I think string theory has been a rich source of material that has kept so many people deeply engaged in moving the frontier forward. From the smallest particles to the grandeur of the cosmos, science has always been our tool to peel back the layers of the unknown, to illuminate the darkness of ignorance with the light of understanding. One thing is certain, the pursuit of science never ends. Each answer uncovers new questions, each revelation leads to new mysteries. We move forward in our journey, understanding that in the grand scheme of the cosmos, we are just beginning to scratch the surface of the vast unknown.